In this masterclass, we're going to discuss centralized and decentralized refrigeration system architecture and why we may or may not adopt one approach or the other. So, a former boss of mine set the applications team a challenge of why we made packs and not condensing units. I mean, we did make condensing units, but we made a hell of a lot more packs. And to be frank, the applications team, mostly being new to refrigeration, and having not gone through the large expansion of supermarkets that happened like 10 years before, we didn't know. So we thought about it. And this is really what stems this masterclass. So in this presentation, we're going to start talking about costs. We're going to talk about energy consumption, and we're going to talk about risks. What we're not going to talk about is which compressor or which refrigerant is best. This is a discussion about concepts. And once we're finished, if you didn't already, you'll hopefully have a greater appreciation of why refrigeration stakeholders have made the decisions they had. Because it's all too common in this industry that the context behind such decisions and actions is rarely documented or well publicized. So, back to basics. How do we choose refrigeration systems? How do we get to the optimal? Well, there's many factors. And first and foremost, it's performance. We have task, product, process, personnel, throughput, temperatures. We have the operational envelopes, design ambient temperatures, room temperatures, etc. We have legislation, regulation, standards, code of practice. Some will kind of guide you, prohibit certain actions, and some will mandate or guide you to particular solutions. Then we actually have, cost, capital expenditure. We have second order costs such as indirect building costs, plant rooms, electrical connections, structural impacts, etc. We have the operational expenditure, energy consumption, taxes and levies, maintenance costs. We have the total cost of ownership, and then we have the impact on cash flow. We also have environmental impacts, direct emissions from within your organization that you have direct control of, such as refrigerant emissions, or otherwise known as Scope 1. You have indirect emissions from the use of energy which you purchase or which you are indirectly responsible for, Scope 2. And then you have any other emissions which you're indirectly responsible for, such as that's required for the production and purchase of goods and services, and the future use of sold products and end of life, such as Scope 3. And then there's all the other environmental effects. Then we have to consider the impacts of failure. What's the likelihood of failure? Is it minor, major, catastrophic? What's the cost of these failures? And then what's the resiliency requirements we have? What's the required uptime? What's the allowable downtime? And then we have things like the constraints. We have spatial constraints, internal, external, lifts, louvers. We have noise constraints. And we have hazard constraints, working at heights, flammability, toxicity, pressurized pipework, exposure and access. And all these factors and more, including personal preference, familiarity, and the conscious bias, influence these selections. But what we're going to do here is, again, focus at costs, environmental impacts, and impacts of failure. So first things first, we're going to define our conditions. So we're going to take a hypothetical ideal refrigerant, and refrigerant choice will have an impact on what systems are possible to adopt. But again, we're just going to go with the concept. So we're going to assume we've got 5 condensing units each with 1 evaporator rated for peak day duty, 1 compressor rated for peak day duty, 1 condenser rated for peak day THR, and 1 expansion device. And then we're going to consider a centralized refrigeration system with all the same items, except the condenser and the compressors are all commoned up. And that fundamentally is centralization. You can have centralization of evaporators as well, and in some respects, centralization of cold stores and multiplex cabinets. But we're not really going to talk about that here. So, the first order problem, peak day. Now, if we look at this, is there going to be any significant difference in performance, in efficiency, and duty between a decentralized system and a centralized system at peak day? And let's keep things simple. There's no significant difference in an ideal cycle in the peak day. But we need to consider that peak day conditions might only occur for a few hours a year, with the vast majority of these of the year being below peak day. Product throughput might only happen during Christmas, for example, and average demand and average other peaks being much lower, like the August bank holiday, for example. And the peak climatic conditions, again, will occur only fleetingly. And let's have a look at this. So this is the annual temperature distribution for 3 cities in the UK. We've got Cardiff, we've got Nottingham, we've got Glasgow. And where's peak day? There's peak day. It is a few hours a year. The average day, it's thousands. And so just some key figures based on this test reference year data from City. 50% of the year in Glasgow is spent at temperatures at or below 9 degrees C. 97% of the year in Cardiff is spent at temperatures below 20 degrees C. And for 99.9% of the year in Nottingham is spent at temperatures below 29 degrees C. For the other 99.99% of the year, we are operating at what I consider peak part load. And this is where our 2 theoretical refrigeration installations will start to operate differently. We're going to start to see lower dry and wet bulb temperatures. We're going to see less product throughput and less associated door openings and personnel and lighting loads, etc. So here we're going to see, in its most basic form, a block diagram about condenser utilization. Each block represents an item of condenser being used, and we have fundamentally the same size condenser, same total surface area, same total volume, for example. And as we can see, at peak day, there is no difference. We both have a mean condenser temperature of 10K. They're thereabouts, so the same duty. But as we just mentioned, we don't have nominal design conditions for most of the year. So, a decentralized system consisting of multiple independent circuits will find itself, as will frankly any refrigerator system, with some of those circuits being off, whether it's because the evaporator is satisfied on temperature, or it's on defrost, or the system has stopped for a myriad of reasons. But what it effectively means is that portion of the site's total heat rejection surface is unavailable for use. But one of the first things to consider with a centralized system, 100% of that total condenser surface area is always available for heat rejection. It matters not if all 5 compressors running or just one. And what does this mean? Well, as we know, or hopefully will know or should know, heat transfer is, amongst other things, governed by the thermal conductivity of the material of the heat exchanger, the total surface area of the heat exchanger, and the temperature difference. And fundamentally, if for one system, for the same THR, the total heat of rejection that is, has more surface area, the temperature difference reduces, which means we have a lower condenser temperature. So here, for the same duty, we have a mean condenser temperature difference of 6K versus 10K. And as we know from previous masterclasses, a reduction in condensing temperature by 1 Kelvin improves COP by 2 to 4%. And so we have a COP improvement of about 16%. And that improvement also gives us some more harder considerations to consider. I say harder. We have a second order consideration. As we know that our COP has improved, so our THR will actually have reduced somewhat, which gives us a further marginal gain in efficiency. Our condenser temperature doesn't have to be that high. We also get maybe a third order consideration. Because we have more surface area, we have a reduced THR, we need less airflow across the condenser. So the average fan speeds will reduce. And as we know, with the power consumed by a fan is proportional to the cube of the change in fan speed. And then there's even a fourth consideration to make. With lower fan speeds, our face velocities are low onto the condenser, which means that we'll probably have, to one degree or another, and in reduction in the intensity of fouling of that surface, resulting in less entrainment of debris onto the condenser face. So there's potentially a lot to be saved here just by having a bigger condenser all in circuit at one time. And whilst we're talking about, particularly in this particular case, a remote direct expansion refrigeration system, we should note that this centralization can be applied to water-cooled, ambient loop-cooled integrals, or as it might be referred to as semi-plugins, because they are still adopting, albeit an indirect, a centralized heat rejection surface.